Alright, my name is Ryan, and it's time to learn about Fourier transforms. Sadly, I'm not talking about some transfiguration spell from Harry Potter.
Well, then what are you talking about?
Well, I'm talking about advanced mathematics. While it might seem like black magic half the time, it probably isn't. The main goal of a Fourier transform is to take a function in the time domain and put it into the frequency domain. There's also a thing called a Fourier series that takes the information from the Fourier transform and uses it to create a sum of sine waves that approximate the original function. You see the effects of this almost every day. If you're a musician, you might be thinking about tuning your instrument. Tuners rely on the shift from the time domain to the frequency domain in order to recognize the pitch that is being played. If you're not a musician, don't worry, you still use Fourier transforms on a daily basis. Fourier transforms are at the heart of signal analysis, and thus are used in even seemingly simple things like making a phone call. Technology aside, your brain is built to actively perform Fourier transforms every waking second of your life. How else would you know that one pitch is higher than another, and thus be able to recognize different words? Net, Fourier transforms are involved pretty much any time we deal with frequency and time.
Well, Ryan, if Fourier transforms are so important, how come everyone isn't taught how to do them?
Just because they're important doesn't mean they aren't hard. There are a few basic types of Fourier transforms. The key differences between them are which squiggly line you use and what bounds you're doing the transform along. If you are receiving discrete information with respect to time, let's say samples from a microphone, you should use sigma notation. If you're receiving continuous time data, then you should use an integral. If you want a continuous versus discrete frequency, it gets a little more complicated. But just remember that continuous frequency involves going from negative infinity to positive infinity, and discrete frequency involves going from 0 to whatever value you want, depending on the precision you want. Now, you might be wondering, that's all fine and dandy, but how do I actually do a Fourier transform? Step 1. Go to whatever browser you use and type Wolfram Alpha Fourier Transform Calculator. Okay, obviously, I'm just kidding. But one of the best ways to learn is by looking at examples. And tools like Wolfram Alpha, or one of the many other Fourier transform calculators, often offer step-by-step solutions that you can look at to see how they work. That being said, Fourier transforms themselves are pretty hard to do, and it's really easy to get overwhelmed when Wolfram Alpha starts throwing things like the Dirac delta function at you. So instead of a Fourier transform, we're going to do a Fourier series. In addition to being just a little bit easier to do, Fourier series are also a lot easier to visualize success with. We can just overlay the results in Desmos and watch the pretty graphs line up. The first thing to think about when doing a Fourier series is that the Fourier series of f of x from negative pi to pi is the thing that I have on screen, where a naught is this, a n is this, and bn is this. Great, now we have a function for a Fourier series with the bounds negative pi to pi. With this newfound knowledge, let's try a simple function like 1 minus x squared. With only a little bit of calculus black magic, we get that a naught is equal to this, a n is equal to this, and b naught is equal to this. And thus f of x is equal to this mess. Now we can make that a little bit nicer and make it look like this, but in essence, voila, we have done a Fourier series. Let's go check our work in Desmos. Now, we run into a little bit of a problem. We can't actually add an infinite number of terms in Desmos. So I'm going to make the upper bound a slider, and we can see the effect of adding more and more terms in the Fourier series. The function we were originally modeling was 1 minus x squared. And our resulting Fourier series, with 100 terms, looks pretty darn close. If we have less terms, it looks less close. And if we have more, it looks more close. I hope you've enjoyed this intro into the world of Fourier. If you want to learn more, I highly recommend the 3 blue 1 brown video from his Essence of Calculus series. There will be a link in the description to that video and a few others that are very useful. Thank you so much for watching, and I hope you have an amazing day.